Assalamu alaikum students, I am Wasim Ikram. This is the fourth lecture in a series of 45 lectures on digital logic design. So how are you today? I hope you have been keeping well. पिछली दफ़ा हमने floating point format पे बात की थी जो कि perhaps थोड़ा सा difficult है. अभी तक जो भी जिन formats पे हमने बात की है वो आप decimal number system में use करते रहें. So थोड़ा सा different है, difficult नहीं है. That's why I keep on saying कि practice करनी पड़ेगी. Practice होगी तो you would get to use these the binary number system. So let's start today's lecture by recalling or reviewing the contents discussed in the last lecture. In the last lecture, we talked about floating point numbers and how we represent floating point numbers. We said if we need to represent very large numbers or very small numbers or numbers having an integer part and a fraction part, we need to use the 32-bit single precision floating point representation. 32-bit floating point representation में the most significant bit is the sign bit. Then you have the 8 exponent bits, and then you have the 23 mantissa bits or the fraction bits. The exponent 8 bits are represented in excess or biased 127 number system. Biased number system बाद में discuss करेंगे. The 32-bit floating point representation allows us to represent very large numbers of the order of 2 raised to power 127. We can also represent very small numbers of the order of 2 raised to power minus 126. जो zero number था, we said if we reserve the exponent to have all zeros, that means the number 0. अगर exponents में सारे ones आ जाएं, that means it's the number infinity. Okay, now let's suppose you have two floating point numbers. Can you straight away add them or subtract them and carry out other arithmetic operations, or do you need to convert them back into the normal binary? Well, you can perform addition using the same floating point format. Let's take an example. You have the number 200 and another number 300. अब exponential form में कैसे represent करते हैं? 200 is 2 into 10 power 2 and 300 is of course 3 into 10 power 2. इन दोनों को अगर add करना हो, what do? 2 plus 3 gives you 5 and the exponent remains the same. So it is 500 or 5 into 10 power 2. Similarly, if you have two 32-bit floating point numbers, so all you have to do is to add the mantissa part, okay, ensuring that the exponents are the same. If they are not the same, then you have to manipulate the decimal point so that the exponent part is the same. So let's consider another example, the number 3000 and the number 200. 3000 exponential form में लिखा जाता है 3 into 10 power 3 and 200 लिखा जाता है 2 into 10 power 2. So of course आप directly इनको add नहीं कर सकते. You have to manipulate the decimal point. So 2 into 10 power 2 becomes 0.2 into 10 power 3. Now you can add 3 plus 0.2 gives you 3.2 and exponent is 3. So similar is the case with the floating point addition. Subtraction कैसे करेंगे? Again, you just subtract the mantissa part, ensuring that the exponent part is the same. If they are not the same, you adjust the decimal point. Multiply कैसे करेंगे? Multiply, again, you simply multiply the mantissa parts and you add the exponent part. Okay, it's 2 into 10 power 2 plus rather multiply 3 into 10 power 2. So the answer is 6, 0, 0, 0, 0. So 6, 10 power 2 exponent, you add, you get 4. Division is again very similar. You simply divide the mantissa part and you subtract the exponent parts. Now, how would you represent larger numbers than 2 raised to power 127 and smaller numbers as compared to 2 raised to power minus 126? Well, there is another floating point format which is known as the double precision floating point format. It uses 64 bits to store a number. The most significant bit is used to represent the sign. The next 11 bits are used to represent the exponent part. The exponent is written in the form of biased 1023 number. As I've said, we would be talking about this biased number system. The remaining 52 bits are used to represent the mantissa part. So you can represent very large numbers or very small numbers using the double precision 64-bit floating point representation. Now, the question arises, how would the digital system, the computer, it would know how to use this number? Is it a 32-bit unsigned representation or is it a 32-bit floating point representation? Well, as I had said before, you have to inform the digital system. How? Well, you have been doing programming, you have learned programming. What do you do when you write a program? पहला step ये होता है कि आप variables define करते हैं. You declare those variables. So you have the variable value, it is of type real. You have a variable ABC, it is of type integer. Now, once you have declared and defined these variables, throughout the program, whenever you call or use the variable value or ABC, or when you execute these variables, the computer knows that the value variable is using the data type floating. The other variable is using the data type integer. So you have to inform the computer or the digital system through instructions. We talked about the hexadecimal number system. Hexadecimal number system, we said, is a base 16 number system. So each digit of a hexadecimal system represents up to 16 values. जो नंबर हैं hexadecimal number system में, you have 0 to 9 and then capital A, capital B, capital C, capital D, capital E and capital F. So F hexadecimal digit represents 15 in the decimal number system. आगे काउंटिंग कैसे करते हैं हेक्साडेसिमल नंबर सिस्टम को यूज करते हुए? वेल, टू रिप्रेजेंट डेसिमल 16 इन हेक्साडेसिमल नंबर सिस्टम यू हैव टू यूज 2 डिजिट्स. मोस्ट सिग्निफिकेंट डिजिट कौन सा है? इट्स 1 हेक्साडेसिमल में. लीस्ट सिग्निफिकेंट डिजिट कौन सा है? इट्स 0. सो 16 डेसिमल इज रिप्रेजेंटेड एज 1 0. 17 डेसिमल क्या होगा? इट्स 1 1. 18 डेसिमल क्या होगा? 1 8. सो इन दिस मैनर यू जस्ट कंटिन्यू एंड यू कैन काउंट इन हेक्साडेसिमल नंबर सिस्टम. हेक्साडेसिमल नंबर सिस्टम यूज क्यों करते हैं? Basically, we said when you write large binary numbers, for example, कोई 40 bit का binary number है. So when you write 40 bits, ones and zeros, you are going to make a mistake. ठीक है, कोई एक 1 गलत लिख दिया आपने, 0 लिख दिया या 1 कर दिया किसी 0 को. Now, to write this long 40 bit binary number in a concise and in short form, you would use the hexadecimal number system. So basically, hexadecimal number system allows you to convert long binary strings into short numbers, of course written in the hexadecimal form. Convert करते कैसे हैं? Well, you write out the string, you divide the string, of course the binary string, into groups of 4 bits. हर ग्रुप ऑफ 4 बिट को आप रिप्लेस कर रहे हैं उसके हेक्साडेसिमल इक्विवेलेंट से. सो फॉर एग्जांपल यू हैव ग्रुप ऑफ 4 बिट्स 0 1 1 1 which is 7. So you would replace that with hexadecimal 7 and so on. Hexadecimal को binary में कैसे convert करना है? Again, it's very easy. Let's suppose you have the number 7F hexadecimal. So 7 is going to be replaced by 4 binary bits 0 1 1 1 and F is going to be replaced by another set of 4 bits 1 1 1 1. Now, you know how to convert from hexadecimal to binary and from binary to hexadecimal. In the real world, we said we use decimal number system, so you should be able to convert from hexadecimal to decimal and from decimal to hexadecimal. वही पुराना तरीका जो हम यूज करते आ रहे हैं डिफरेंट नंबर सिस्टम के साथ. So when you are interested in converting a hexadecimal number into decimal, what do you use? Sum of weights method. वही आप एक एक्सप्रेशन लिखेंगे, solve the expression, you get the answer. डेसिमल को आपने हेक्साडेसिमल में कैसे कन्वर्ट करना है? इट्स द रिपीटेड डिवीजन मेथड, राइट? सो रिपीटेड डिवीजन में किसके साथ डिवाइड करेंगे? 16 के साथ, राइट? सो यू हैव सम डेसिमल नंबर, यू डिवाइड बाय 16, यू गेट ए क्वोशिएंट वैल्यू, यू गेट ए रिमाइंडर. रिमाइंडर आपने नोट कर दिया, क्वोशिएंट को दोबारा से आप 16 से डिवाइड कर रहे हैं उसमें. सो यू कीप ऑन डिवाइडिंग अंटिल द क्वोशिएंट वैल्यू बिकम्स 0. दैट इंडिकेट्स एंड ऑफ कन्वर्जन. वो जो रिमाइंडर्स आपने नोट किए हैं वो दोबारा से लिख लें. दैट गिव्स यू द हेक्साडेसिमल इक्विवेलेंट ऑफ द डेसिमल नंबर. नाउ, if you use these hexadecimal numbers, then of course you can perform multiplication using hexadecimal numbers, division, subtraction and addition of course. So we did some examples, I don't need to repeat that. Addition in hexadecimal would of course generate carry rather when you add decimal numbers, carry is generated there. When you add binary numbers, carry is generated there. Similarly, if you subtract 2 hexadecimal numbers, you might need to borrow. Let us look at the octal number system. The octal number system is a base 8 number system. So each digit of an octal number system would represent values from 0 to 7. You cannot represent 8 in octal. So what do you do when you need to write 8? Basically, you use 2 digits. The most significant digit would be a 1 and the least significant digit would be a 0. 9 कैसे होगा? 1 1. 10, it's 1 2 and so on. So the next set of 8 numbers, decimal numbers, would be represented using 2 digits of the octal number system. The most significant digit would be 1 and the least significant digit would be starting from 0 and going all the way up to 7. The next number would start with 2 0, then 2 1 and so on. Let's have a look at the octal number system. The first slide would show the octal representation of decimal numbers and the second slide would show the counting in octal. The octal number system has 8 values. It is a base 8 number system. So the values in the octal number system are from 0 to 7. So they in fact represent the first 8 values of the decimal number system as seen in the table. Binary equivalents of the octal numbers can be represented using 3 bits because we have a range of 8 numbers. So the binary equivalent 000 represents octal 0 and binary 111 represents octal 7. The table shows octal equivalents of decimal numbers 8 to 31. Octal number 7 has the largest value. To represent decimal 8, a 2-digit octal number is used. The most significant digit is a 1 and the least significant digit is a 0. So the decimal numbers 8 to 15 are represented by the 2-digit octal combination. Similarly, the decimal numbers 16 to 23 are represented by another 2-digit octal combination. The most significant digit is 2 and the least significant digits vary from 0 to 7. And similarly for higher octal decimal numbers. Why do we need to use the octal number system? Basically, reason uska wahi hai jo hexadecimal number system mein tha. When we write large or long strings of binary numbers, error ke chances hote hain. So to represent long binary strings in a compact, concise form, you use the octal number system. But since we have the hexadecimal number system, so octal number system is not very frequently used. Anyway, since we are discussing the octal number system, let's look at converting from decimal to octal, octal to decimal, and octal to binary, and binary to octal. So let's first start by looking at the conversion from binary to octal. कैसे होगा? Well, वही तरीका है जो हमने hexadecimal conversion के लिए इस्तेमाल किया था. You write out the binary string, उसको divide कर दें into groups of 3 bits, not 4 bits, because this is a base 8 number system. And remember, 3 bits, binary bits, represent a single digit of the octal number system. So you divide the binary string into groups of 3. Then what do? You just replace that binary group of 3 bits by its equivalent octal number. So 011 hai, it would be replaced by octal 6. 101 hai, that would be replaced by octal 5, and so on. Octal numbers can be converted into binary. How? Again, वही method use करेंगे जो आपने hexadecimal से convert करने के लिए इस्तेमाल किया था. So you have the number, let's say 76 octal. So 7 is going to be replaced by its binary equivalent 111. 6 is going to be replaced by its binary equivalent 110. So you have a 6-bit binary equivalent of a 2-digit octal number. ये बाद में हम इसकी slides वगैरह examples देखेंगे. Let's consider converting octal number system into decimal number system. Again, there are 2 methods. One is the indirect method. The indirect method would be you convert from octal to binary and then binary to decimal. The other standard method is the sum of weights method. So you have an octal number, you write out an expression, usko jab aap solve karenge, you would get the decimal equivalent. The base system is 8, so base number 8 use ho raha hoga. How do you convert from decimal to octal? Again, you have the indirect method where you convert to binary and from binary to the other number. The standard method is the division by 8 or the repeated division by 8 method. So you have a decimal number which you are trying to convert into octal. What do? You divide it by 8. You get a quotient value, you get a remainder value. You note down the remainder, you divide the quotient again by 8. You keep on doing this until the quotient value becomes 0. That means end of conversion, you just write out the remainders and that would give you the octal representation of the decimal number. Now, you can in fact perform all arithmetic operations using octal number system as you did with the hexadecimal number system. So you can add 2 octal numbers, you can subtract octal numbers, multiply, divide. वही rules apply होंगे जो decimal में, binary में, hexadecimal में apply हो रहे हैं. When you add, a carry might be generated. When you subtract, you might need to borrow something from the next higher digit. So let us look at the examples of these conversions, the addition and the subtraction. Consider the binary to octal conversion first. Consider the 21-bit binary string which is to be converted to octal. The 21-bit binary string is divided into groups of 3 bits starting from the least significant bit. 7 groups of 3 bits are formed. In the next step, each group of 3 bits is replaced by the equivalent octal digit. The result is a 7-digit octal number. Now consider another example. Consider the 13-bit binary string which is to be converted into octal. The 13-bit binary string is divided into groups of 3 bits starting from the least significant bit. Now 4 groups of 3 bits are formed and an incomplete 5th group with a single bit is formed. What do? We add 2 most significant 0 bits in the 5th group to make it a complete group. Now each 3-bit group is replaced by the equivalent octal digit to complete the conversion. So the original 13-bit binary number is now represented as 13351 in octal. Let's now consider the octal to binary conversion. The octal number is 1726. each octal digit is replaced by its equivalent 3-bit binary number. Thus, octal 1 is replaced by 001, octal 7 is replaced by 111, octal 2 is replaced by 010, and octal 6 is replaced by 110. Now let us consider the sum of weights method to convert an octal number 4037 to decimal. An expression in terms of the base number 8 and weights is written, as can be seen. The expression is solved to give 4 sum terms: 2048, 0, 24, and 7. The 4 terms are added to result in the number 2079, the decimal equivalent of octal 4037. Now let us consider the conversion of a decimal number into an equivalent octal number. The decimal number is 2079. It is divided by 8, which results in a quotient value of 259 and the remainder 7. The remainder 7 is noted and the quotient 259 is divided by 8. 259 divided by 8 results in a quotient value 32 and a remainder value of 3. The remainder 3 is noted and the quotient 32 is divided by 8. 32 divided by 8 results in a quotient value of 4 and a remainder 0. The remainder 0 is noted and the quotient value 4 is again divided by 4. This results in a quotient value of 0, which indicates the completion of the repeated division by 8 method. The remainder 4 and the 3 remainders noted earlier represent the 4-digit octal number 4037. Let us now consider octal addition. Consider the addition of octal numbers 7602 and 4771. The two octal numbers are added by first adding the two least significant octal digits 2 and 1. The sum of the two octal digits is 3. The next two octal digits 0 and 7 are added and the result is 7. The octal digits 6 and 7 are added next. The answer in decimal is 13, which is represented as 15 in octal. Thus, the sum is octal 5 and the carry is 1, which is carried over to the most significant digit. Adding the most significant octal digits 7 and 4 along with the carry results in decimal 12, which is equivalent to octal 14. The sum is 4 and carry of 1 is carried over to the 4th octal digit position. The sum is 14573 octal. Consider the subtraction of octal 4771 from octal 7602. The two numbers are subtracted by first subtracting the least significant digits octal 1 from octal 2. The difference is octal 1. Next, octal 7 is subtracted from octal 0. A borrow is required from the next most significant digit. Borrowing a 1 means subtracting octal 7 from octal 10, which is decimal 8. The difference is octal 1. The octal number 7 is subtracted from octal 5 instead of octal 6 in the second digit position, as a 1 had been borrowed from octal 6. To subtract octal 7 from octal 5 requires another borrow from the most significant digit 7. Thus, subtracting octal 7 from octal 15 results in a difference of 6. The most significant digits are subtracted to result in 2. The difference of octal 7602 and 4771 is octal 2611. Up till now we have looked at 4 different ways of representing binary numbers. One of them was the floating point, the remaining were the normal binary. There are again several other alternate ways of representing binary numbers. Let us have a look at those alternate methods. The alternate methods which we would be discussing, the first method is the excess code, the second method is the BCD code, and the third alternate way of representing binary numbers is the gray code. What is the excess code? Excess code or biased code is used by the floating point numbers. Why did we use the biased number or the code with the floating point numbers? We used it to represent the negative as well as the positive exponents. We had two options: either we increase the exponent bit by 1 to have a positive or negative sign, or just to keep it as 8 bits and use the excess code method. So let's consider an example before we look at the actual excess code. Consider the number -1, 0 and 1 in decimal. How would you represent this in binary? Sign binary use करना होगा क्योंकि negative number भी है, positive number भी है. So positive 1 is represented as 0, 1. 0 signifies positive and 1 is the magnitude. The 0 number itself is represented as 0, 0. And negative 1 would be 1, 1. 1, the most significant one signifies the negative number, and the least significant one represents the magnitude of negative 1. Now, if you look at the 3 binary representations, you cannot compare them, right? Now, 1, 1 actually means 3 in unsigned binary, right? So, it would have been better if -1 had been represented by bits 0, 0, 0 had been represented by bits 0, 1 and 1. Positive 1 had been represented by 1, 0. So you have a smooth scale through which you can compare. So 0, 0 is of course less than 0, 1, which is in fact a 0. So the excess code is used to give a uniform scale to positive number and negative numbers. Let us consider an example. We are going to be using an excess 8 code to represent numbers between minus 8 to plus 7. Consider the decimal number range positive 7 to minus 8. These positive and negative decimal numbers can be represented by the 2's complement representation, as can be seen in the table. The magnitude of positive and negative numbers can not be easily compared if the numbers are represented in 2's complement form. The decimal number range plus 7 to minus 8 is represented using an excess 8 code that assigns 0, 0, 0, 0 to minus 8, the lowest number in the range, and 1, 1, 1, 1 to plus 7, the highest number in the range. Now, excess code 8 or excess 8 code is obtained by adding number to the lowest number minus 8 in the range such that the result is 0. So now the number which you add to the lowest number minus 8 to give you a 0 is the number 8. So that's how you get excess 8 code. Minus 7 is represented as a 1 because 8 is added to minus 7, the result is 1. So you write 0, 0, 0, 1, which is the excess 8 notation. The resulting code which you get is known as the excess 8 code or biased 8 code. We've just seen an example of excess 8 code. Excess 8 code is in fact a binary code which has been shifted by 8. The excess or biased 127 code which we use to represent the exponent part in the 32-bit floating point representation is in fact again a binary code which has been shifted by 1 to 7. Now let us look at another representation, the BCD code. Now, you must have traveled via train. So when you go to a railway station, you see those huge clocks, digital clocks, where time is shown as decimal digits. You must have also seen these clocks in buses. So now, the clock circuit is a digital circuit, which sends out or displays time on a 7-segment display. Now, let's suppose you need to display the time 12 o'clock. So how do you display the 2 digits? Well, you have to send out some binary code to display the digit 2 and send out some binary code to display the digit 1. Now, since you are displaying decimal numbers 0 to 9, you cannot go beyond that, right? If you need to display 12, then you are displaying 2 digits, right? Each digit can change from 0 to 9. So now, how many bits do you require to display a single decimal digit from 0 to 9? Well, you require 10 different codes, binary codes. So how do you represent decimal digit 0? Bits 0, 0, 0, 0. How would you represent the highest decimal number 9? Binary number 1, 0, 0, 1. Now, you can get more combinations if you use 4-bit binary. So you can also have a number 1, 1, 0, 0, which is in fact 12. But you do not use binary codes higher than 1, 0, 0, 1. So the BCD representation only uses the first 10 binary codes starting from 0000 up to 1001. Now, as I said, where are they used? These binary codes or the BCD code is used to display decimal numbers. Now, if you learn to use these BCD codes, then you can of course represent decimal digits using these BCD codes. You can in fact perform additions and subtractions using BCD numbers. Let us have a look at an example which shows us how we can add 2 BCD numbers. Let us first consider the BCD code. As I said earlier, BCD code represents the decimal digits 0 to 9. So a 4-bit BCD code 0000 represents decimal 0 and 1001 represents decimal 9. A 4-bit binary code can represent up to 16 different values. The first 10 binary codes represent the decimal numbers 0 to 9. The remaining 6 codes 1010, 1011, 1100, 1101, 1110 and 1111 are considered to be invalid BCD codes. Consider the addition of two 2-digit BCD numbers 23 and 45. BCD numbers are added using binary addition method resulting in 68. Now consider the addition of two 2-digit BCD numbers 23 and 49. Adding least significant digits 3 and 9 results in 12, represented as 1100. Now 1100 is an invalid BCD digit. Secondly, adding 3 and 9 in decimal should result in 2 as the sum and 1 as the carry. The BCD result 0110 1100 is equivalent to 62, which is incorrect as the carry generated by the addition of the least significant digits has not been considered. When addition of BCD digits results in an invalid BCD number or a carry, the number 0110, which represents decimal 6, is added to the result. Reconsidering the addition of BCD 23 and 49, the addition of digits 3 and 9 results in 1100, an invalid BCD number. A 0110, which is decimal 6, is added, which results in 0010, and a carry, which is added to 0110 to result in 0111. Now, the BCD number 0111 0010 represents 72, which is the correct answer. We have just seen the BCD code. BCD code represents decimal digits from 0 to 9. So, the binary code 1010, which represents decimal 10, is invalid. So, only the first 10 binary codes are used. BCD in fact stands for binary coded decimal. The third representation, the gray code representation, let's have a look where do we use this gray code. Now, if you look at the binary code, when you, let's suppose, count from 2 to 3, how many bits change? Only the first or the least significant bit changes. Let's suppose you are counting from 7 to 8. How many bits change? Well, 7 is 0, 1, 1, 1 and 8 is 1, 0, 0, 0. 4 bits have changed. Now, in certain electromechanical applications of digital systems, you would like to keep the bit change to 1 when you count up or down to the next successive value. The gray code is a binary code which allows you to represent successive numbers where the bit change is limited to 1. So, for example, when you count from 3 to 4 or from 3 to 2, the changes in bits would be limited to 1. As I've said before, you need to restrict the bit change to 1 when you count from one number to the other successive number. Let us have a look at an example which explains the utility of the gray code. But before that, I would like to mention that the gray code is not a positional code. Binary code, we said, was a positional code because each bit represents a certain value. Gray code is not a positional code. Now, let's have a look at the example. Let us consider the 3-bit binary code and the 3-bit gray code representing the decimal numbers 0 to 7. The binary code is a positional code and the 3 bits starting from the least significant bit have the weights 1, 2 and 4. The gray code is not a positional code. However, the change from one value to the next using the gray code guarantees a single bit change. So, as you can see, counting from 0 to 6, the change between successive representations or successive numbers is limited to a change of only 1 bit. Consider the example of shaft encoders that best explain the utility of the gray code. The diagram shows a disk connected to the shaft of a rotating machine. The shaded areas on the disk indicate conducting strips connected to plus 5 volts. The non-shaded area indicate non-conducting strips. The 3 stationary brushes A, B and C touch the surface of the rotating disk. The 3 brushes are connected to 3 LED lamps through wires. As the disk rotates, the brushes come in contact with the conducting area and the insulated area. The 3 LEDs display the position of the rotating shaft in terms of 3-bit numbers. Consider the disk on the left. If the disk on the left rotates in the anti-clockwise direction by 45 degrees, the brush A comes in contact with the non-conducting strip. Thus, LED connected to brush B lights up indicating binary 010. Consider the disk on the left. If the disk on the left rotates in an anti-clockwise direction by 45 degrees, the brush A comes in contact with the conducting strip at 5 volts and turns on the LED indicating binary 001. If the disk continues its rotation and after another rotation of 45 degrees, brush B comes in contact with the conducting strip and brush A comes in contact with the non-conducting strip. Thus, LED connected to brush B lights up indicating binary 010. Thus, at any instant of time, the LEDs indicate the angular position of the rotating shaft in steps of 45 degrees. Assume that the 3 brushes A, B and C are not aligned properly and brush B is slightly ahead of brushes A and C. Now, if the disk rotates 90 degrees from its start position, brush A is in contact with the conducting strip, brush B, due to its misalignment, is in contact with the conducting strip and brush C is in contact with the insulated strip. Thus, when the disk rotates, the LEDs will show a 001 followed by a 011 for a short duration when the disk rotates from 90 degrees to 91 degrees, and then it would display 010. Thus, due to misalignment, the count value jumped from 1 to 3 and then back to 2. Consider the disk shown on the right. The conducting and non-conducting strips follow a gray code pattern 000, 001, 011, 010, 110, 111, 101 and 100, representing decimal numbers 0 to 7. Now, even if the brushes are misaligned, the LEDs would always display the correct count value. We have just looked at an example of the gray code. We might be looking at other examples of gray code during the course of the study. Up to now, we have been looking at only numbers, positive numbers, negative numbers, numbers having fraction part, numbers having an integer part. Now, we said in the beginning, in the first lecture, that computers can be used to write documents. You have been writing programs, so in your program you have text information as well as numbers. So how do you represent capital letter A, small letter B, number 0, number 9, full stop, comma, question mark? So all these characters have to be again representing in binary, because as we know, digital systems only recognize binary. Now, the representation which is used to represent text punctuation marks is known as an alphanumeric format, or the alphanumeric representation. The most commonly used representation is the ASCII representation, the American Code for Information Interchange. It is a 7-bit format. So how many codes do you think it can represent? 2 raised to power 7 gives you 128 unique codes. Now, 128 character ASCII code is divided into capital letters, small letters, numbers, punctuation marks, and some control characters. Let us have a look at the ASCII table. Consider some of the ASCII codes that represent the numbers 0 to 9. The ASCII code 011 0000, which is also equivalent to 30 hexadecimal, represents the number 0. The ASCII code 011 0001, which is also equivalent to 31 hexadecimal, represents the number 1. Similarly, the ASCII code 011 1001, which is equivalent to 39 hex, represents the number 9. How do we represent the capital alphabet letters and the small alphabet letters? Well, the lowercase alphabet letters A to Z are represented by ASCII codes 1100001, which is 61 hex, which represents small letter A, up to 1111010, which is 7A hexadecimal, and it represents the lowercase character Z. The ASCII code 1000001, which is equivalent to 41 hex, represents the uppercase alphabet A, and the code 1011010, which is equivalent to 5A hex, represents the capital character Z. The 32 control characters are represented by ASCII code 0000000, which is 0 hex, up to 0011111, which is equivalent to 1F hex. These control characters are not seen on the screen. They are simply executable codes. The 7-bit ASCII code is known as the alphanumeric code because it is used to represent alphabet characters as well as numbers. Now, 128 different characters is not enough. You would like to represent or write some other characters, some graphical characters. So we have another version of the ASCII code which is known as the extended code. The extended ASCII code is an 8-bit code. So how many codes can we uniquely represent using the extended ASCII code? Well, it is 2 raised to power 8 or 256 unique codes. The 128 codes which we have just looked at is a standard, whereas the extended version, the remaining 128 codes, are not a standard. Different vendors use different versions of the extended set. Now, even an 8-bit ASCII code which allows you to represent up to 256 different characters is not enough. On your computers, you must have seen some Urdu characters or Arabic characters. So how do you represent such characters? There are other languages, Japanese, Chinese. Well, there are other standards. One of them is the Unicode. The Unicode is a 16-bit code. So how many characters can you represent a Unicode? Well, 2 raised to power 16. So nearly 64,000 different unique characters can be represented using the Unicode. There are other codes. Now let us look at error detection. In the first lecture, we mentioned that digital systems are very reliable systems. But even then, when you store information or when you transmit information, there are chances that the information is going to be it is going to be corrupted. Now, what do you do? Well, in order to have secure information, you need to have a mechanism to detect errors if they have occurred, and perhaps try to remove those errors. Now, one simple method of detecting errors is using the parity bit. Let's consider an example. Let's suppose you and your friend set up a piece of wire, a communication link, and you send some numbers, let's say 0 to 7, to your friend across that wire link. You agree that each number is going to be represented in an 8-bit binary format. So you would be sending 8-bit numbers to the other end. Your friend at the other end would read the number and send back its 2's complemented form. Now, let's suppose you send the number 7, and your friend should be receiving the number 7, of course, in binary. Now, how would you ensure that your friend has received the correct number? It is 7 and it is not 8. To ensure correct exchange of information between you and your friend, you decide that you would only be sending numbers which have an odd number of ones. So that means you would send the number 1. How many ones does it have? An odd number of ones. You could send 2. How many ones does it have? Again, an odd number of 1. You cannot send 3 because there are 2 ones, so it is an even number of ones. Well, this particular requirement restricts the number which you can exchange. Well, why not use a better method? The sender, you count the number of ones in your message. If it's an even number of ones, you append an extra bit and set it to either 0 or 1 so that the total number of bits add up to an odd number. So, for example, you are sending the number 3. How many bits do you have? You have an even number of bits. So you append a parity bit, which is known as the odd parity bit, because you would be setting that parity bit to 1 so that the total number of bits add up to an odd number. So you would now be transmitting 9 bits, the 8-bit number, 3, and the parity bit. Your friend would receive the 9 bits. He would count the number of bits in that message. So if it's an odd number of bits, then that means the message is correct. No bit has been corrupted. If the number of ones in the message turns out to be an even number, that means some error has occurred. So now you as a sender would be generating 8-bit numbers, counting the number of ones, setting the parity bit to 1 or 0 so that the total number of ones in the message comes out to be odd, transmitting the number to the other end. Your friend at the receiver would be counting the number of ones in the message, including the parity bit. If it turns out to be odd, then the message is correct. If it turns out to be even, then the message is incorrect. Then perhaps he can send you a signal requesting you to send or resend the message. You could use the even parity method. In the even parity method, you and your friend decide that the number of ones which you would be sending would be an even number. So the procedure is the same. You would generate a number, an 8-bit number. You would count the number of ones. If it is an odd number, then you would attach a parity bit set to 1 so that the total number of ones come out to be even. So you would be sending these 9-bit messages. At the other end, the receiver end, your friend would be counting the number of ones. If they are even, then the message is correct. If they are not even, the message is incorrect. So we either use the odd parity method or the even parity method to detect 1-bit errors. Let us have a look at an example which explains this parity bit method of detecting errors. Consider an example of odd parity error detection. The original data which is to be sent or which is to be stored is 1001 1010. With odd parity, the total number of ones should be an odd number. So how many ones do we have in the original message? An even number. There are 4 ones. So you append a parity bit and set it to 1. So the total number of ones now becomes an odd number. Now let's suppose this 9-bit information is stored or transmitted to a remote location, and at the remote location the message has changed to 1101 11010. The most significant bit is the parity bit. How many ones do we have in the message? 6. Since we are using the odd parity scheme, the total number of ones in the message should have been odd. So this indicates a single bit error. Now let us consider that a 2-bit error occurs. So we send the message, the original message, with the odd parity bit 1100 11010. Let's suppose the 2 bits which have been underlined change. What do you get at the receiver end? The total number of ones is still odd. So have we detected an error? No. So if a 2-bit error occurs, we are not able to detect an error. Now let us consider the third case. We send the original message with the parity bit and a 3-bit error occurs. The 3 bits which change due to an error are underlined. Now, how many ones do we receive at the receiver end? The total number of ones which have been received in the 9-bit message are 4. It is an even number. So that means an error has occurred. But we are not sure if a single bit error has occurred or a 3-bit error has occurred. But we know that an error has occurred. So in summary, by using a parity bit, we are able to detect 1-bit error, a 3-bit error, a 5-bit error, or a 7-bit error. But we are unable to detect even bit errors. For example, 2-bit error occurs, we are not able to detect that. A 4-bit error occurs, we are not able to detect that. We have just looked at an example of odd parity, which is used, of course, to detect a single bit error. We said using the parity bits, we cannot detect even bit errors. We end today's lecture here. Before we end, let us quickly summarize the topics which we have discussed. We started with the octal number system. We said it's a base 8 number system, and it is basically used to represent large binary strings in a short, concise form. We talked about alternate ways of representing binary numbers. We talked about the excess code, which we use in the floating point implementation. We talked about BCD code, which is used to represent decimal digits in binary. Again, applications are to display decimal digits on 7-segment displays. We talked about a gray code, which allows only 1 bit change when you count to the next successive value, the upper value or the lower value. We also talked about alphanumeric codes, the ASCII code. The alphanumeric or the ASCII code allows you to represent numbers, alphabet characters, punctuation marks, and some control characters. Towards the end, we looked at an error detection scheme which uses the odd parity method or the even parity method to detect 1-bit, 3-bit, or 5-bit errors. Let us stop for today. With today's lecture, we have finished our discussion on number systems. As I have been saying before, keep practicing with the binary number system. You should be able to relate to binary numbers as you do with decimal numbers. So see you next time. Khuda Hafiz and Assalamu Alaikum.